All right, so this is the answer key to the hard water task. By now, you should have read the background. You should have taken a shot at this simulation. The simulation is right on this screen right over here, and I'm going to walk through this on a video form so you have the answers and support that you need. Remember, the goal of hard water is to figure out how much calcium we have. And so the first task we had here is what substance is your calcium source? And so I'm going to go to my simulation. I have a calcium source, that's CaCl2, and now I have calcium in my water. For now, I'm just adding one click, but you could add however many you want. I'm going to come back here and model that in my particle diagram. Let me get rid of these so they don't show right now. One Ca2 plus and two Cl minuses, right, based off of what I'm seeing right over here. I'm going to hit reset. And then this says, what's your carbonate source? Carbonate right here is where is it? Right here, CO3 2 minus ion. And so I look for that. I see a CO3 right over here. And so this is going to give me, I click twice, but if you only click once, it's going to give me two sodiums and one carbonate polyatomic. So over here, I'm going to model two sodiums and one carbonate polyatomic. My cation is always my positive ion right here. My anion is always my negative ion. Even though I have two, I only take one of them. Over here, my cation is my positive ion. Even though I have two, I only take one of them. And my anion is CO3 2 minus. All right. And now here comes the crisscross rule. The crisscross rule, when you're doing Na and Cl, that gives you NaCl. That's quite simple. They both have a charge of +1. You notice that your calcium and your carbonate have a +2 and a -2 charge. And so therefore it only takes one of each to cancel each other out. And so after you do your crisscross rule, you're going to end up with CaCO3. A lot of students put a CaCO3 2 down here, and that's incorrect because that would mean that you have two of these anions on a total of -4 charge with only one +2 charge, and that doesn't cancel out. So you're just going to have a CaCO3. And because we just have one polyatomic, we technically don't need the parentheses, but you can keep it there if it makes you feel better. So now these are my products. I'm going to write them both here. NaCl plus CaCO3. And now your job is to figure out what is the precipitate. And so I go back to my rule. And my rule says any compound that has potassium, sodium, ammonium, nitrate will be soluble. And that means it does not form a solid or a precipitate. And so if I go back to my drawing or my equation here, this has a sodium in it, and so it is not going to be my precipitate. So I'm going to label that with an AQ, which means this substance right here has to be my precipitate. I check to see if everything's balanced. I see two chlorines over here. So I'm going to put 2 NaCl over there, because remember, I can't adjust the subscripts, only the coefficients. And over here, I have 2 sodiums. So this 2 takes care of that. Remember, this 2 is like a distributive property, right? So it goes to the sodium and the chlorine, and everything else looks good to go. I can also check this balanced equation by this, doing it actually on here. So let's say I have my sodium carbonate right here. I add my calcium source back in. And now if I let everything play out, you'll realize that the calcium and the carbonates attract to each other to form CaCO3, which is exactly what we have in our equation. And the NaCl is left floating as spectator ions. And so that's how we know the NaCl is aqueous, right? They have the option to bond to each other, but they don't because their attraction to the water is stronger than their attraction to each other. And so this is exactly what my equation represents. It represents the CaCO3, which is solid. It represents the NaCl, which are aqueous. And so now, when I go to figure out my net ionic equation, I start splitting things apart. So this calcium chloride, if I reset, breaks up into 1 calcium and 2 chlorine, which is what I've shown right over here, 1 calcium and 2 chlorine, right? A lot of students have this, they'll do Cl2 minus, and that actually doesn't capture the picture. The picture is each one of these is Cl, and there happens to be two of them. And so you don't need the Cl2. Over here, your NaCO3 or your Na2CO3 goes to two NAs and one CO3 2 minus, and they're kind of floating around with each other. And so now I put two NAs and the CO3 2 minus. What I like to do here is always just bring down my solid because I know that's not going to dissociate. And so that formula just stays the exact same. And then I got to figure out, well, what does this split into? Well, it's going to split into 2Na plus 2Cl minus. Remember that 2 is like the distributive property in math. And so this 2 goes to both. And the way I see that here is two Cl's and two NAs separately floating around. And so now I'm going to highlight my spectator ions. These are spectator because they show up on both sides of the equation. And what I'm left with is Ca2 plus CO3 2 minus gives me CaCO3 as a solid. And this becomes my net ionic equation. I can be more specific and write aqueous here. So I'm telling the reader that they're aqueous in solution. And my spectator ions right here are just Na plus, just Na plus and Cl. Right, even though we have two Cl's and two NAs as spectator, we just need one of each when we talk about which ones are the spectator ions. So that completes slide 4. All right, let's go to slide 5. And for this, I'm going to restart my simulation. Let's say I have 2 clicks of CaCl2s. I want to get all the calcium down. And so if I just do 1 click of Na2CO3, I'll notice that I get one of the calciums down to precipitate, but the other one is floating around. And so I need a second Na2CO3 to come along, and so that the second calcium ion gets precipitated. That's kind of what this net ionic equation tells you. It tells you for every calcium, you need one carbonate to form CaCO3. And so what you should realize on this slide is that the number of CaCl2 particles are the same. The number of calcium, I'm just going to write the word, calcium chloride particles is the same as the sodium chloride particles. And this is represented in the net ionic equation. All right, and so over here, suppose you had 3 clicks of CaCl2 particles and 4 clicks of Na2CO3. What would be the limiting? What would be the excess? Well, CaCl2 would be the limiting reactant, and the excess would be Na2CO3, right? And so your particle diagram would have extra Na and extra CO3 floating around, right? Because those are extra clicks. Suppose the concentration of calcium chloride is 0.02. What would you expect to happen if only 0.015 molar of Na2CO3 was added to the water sample? So I would expect that there is extra calcium ions and chlorine ions floating around, and some of the calcium would precipitate with the carbonate, but there is not enough carbonate to bring all the calcium to a solid, right? And that's just because you have less sodium carbonate, and over here we established that you need the same amount. So this question is getting at your understanding of what the particle diagram would look like. All right, over here it says give me an image of your screenshot, so you can take a screenshot of your diagram right here and pop that over onto your slide. Let's Let's make that a little smaller. All right, and then name two other substances that could be used to precipitate calcium ions. Well, let's take a look. And if you don't know, then this is a fine place to play around. But if you have calcium ions here, what happens if you add K2SO4? Well, the calcium ions go over and bond to the sulfate, and they also drop. So you could definitely use K2SO4, and you could use Na2SO4 because it also has a sulfate ion, right? And so you you could say K2SO4, K2SO4, and Na2SO4. Because when the calcium bonds with the sulfate, it forms a precipitate. All right. And the reason that happens is because, once again, in that compound, we don't see any of these substances. And so we know it's going to form a precipitate. The last question here has you walk through a calculation. Suppose that in this, all of this calcium carbonate right here that you're getting as a precipitate amounts to be 0.037 grams of calcium carbonate. How many grams of calcium do you have in this sample? So remember, calcium is the indicator of water hardness, but here we have CaCO3. And so remember, we want to isolate for the grams of calcium. And so the way that you would go about doing that, and I'm not going to do all the math out here, but this video kind of helps you along. You would start with 0.0037 grams of CaCO3. Let's make that a little bit bigger. And then you would first convert to grams of CaCO3. So 1 mole is about 100 grams, and that would give you 0.00007 moles of CaCO3. And that number comes right back down here. And now you're going to convert to moles of calcium. And in CaCO3 right here, I have 1 mole of calcium in 1 mole of CaCO3, right? It takes 1 particle of calcium to bond with 1 particle of CaCO3. So I can come up with this mole ratio. That's just going to give me 0.0037 moles of, now my units change, of calcium. I bring that down. And I multiply by calcium, I think is 40 grams. And this is 1 mole of calcium. And 40 times 0. Oh, actually, I left off a couple of zeros. So we'll have to. Yeah, need to add in 2 zeros here. So 40 times 0.000 is 0.00148 grams of Ca. All right, and that's how you would figure out the grams of calcium. Hopefully this video helped walk you through. Hopefully I was able to hit some misconceptions, and if you have any questions, feel free to leave them as private comments.